largely from fermentation of the collection system. The primary clarifier may or may not have an on-site fermenter. You may or may not truck some in or bring them in, but all of those have been possibilities. This is actually a picture of, remember that plant that I showed you at Walt Disney World at Reedy Creek, where they had the nitrification problem, where the low pH, and they turned off the aerators to get denitrification? One of the other things that was like, I'll be darned, look at that they discovered was when they turned those aerators off to get denitrification, it created, this was their total phosphorus in their effluent. What happened to the phosphorus in the effluent when they created an anaerobic zone right within that reactor? Boom. Yeah. So they had phosphorus bugs that were just waiting for the condition to switch it on. It's quite remarkable. Mother Nature has such a ubiquity, so many different ever-present organisms waiting to rise to the bait, if you will. This is just showing a effect of adding acetates to stimulate for VFA uptake and release, that we get faster uptake than following supplemental VFA addition. The term secondary release is referring to the idea that once the phosphorus is on board on the microorganisms, when they get into anaerobic conditions, it's not very stable. It likes to leak out. And so secondary release then is the leakage of phosphorus that was otherwise contained within the cell. And when it's leaking out that phosphorus, remember that that phosphorus that was on board was the power that they had to take up carbon when they get back around again. So they, you know, to the degree that they've lost phosphorus storage, it is the mirror image of that is the reduction in the ability for uptake or for release then when it gets into the anaerobic zone. And if it hasn't released in the anaerobic zone, it didn't take things up in the, it won't take it up as much phosphorus when it gets over to the aerobic side of things. So it really is compromising the whole cycle. So optimizing performance then ends up coming down to largely eliminating the nitrates from the anaerobic zone so that we get the right release going. Although, you know, I did mention that now there are denitrifying PAOs that are able to do some uptake and storage of phosphorus and utilize nitrate for that purpose. So they're not as efficient as at least my understanding is, but they do somewhat modify our hard and fast rules about nitrate scrubbing prior to anaerobic. Keep the oxygen down, absent, ensure that we have adequate carbon source of BFAs, and try to limit fermentation. And I'm sure Leon's going to improve our understanding greatly on the RAS fermentation aspects of improving performance. And I haven't talked with you, Leon, yet about a question that Dan has here from North Texas, but you're going to, I'll tee it up to you at the lunch breaks, because it's related to what happens with the phosphorus on the RAS. And I know that you've got a lot of experience now in optimizing how RAS is handled actually to enhance the whole cycle. So I'm going to punt that one to you. Aerobic zone, keep the oxygen adequate for the uptake and storage, because that's an aerobic function. Keep the pH neutral, and higher is better. Not that you can necessarily control pH, but from the GAL-PAL competition standpoint, the GAOs are more acidophilic. They like a pH lower. So there you go. BioP considerations. Then we've talked about. I think we've talked about all these except SRT. So SRT, we've been talking about that over the last day and a half now, about it's the means by which we're kind of selecting for organisms based on their ability to divide as fast as they need to stay up with the wasting rate or the washout rate. And I think I'm sure I mentioned this yesterday, that when we're selecting SRT, we have to default to the slowest growing organisms if we're looking at full BNR. Well, that's clearly the nitrifying fraction. And so that's always going to be the default answer on SRT. We can get very good peak PAO competition at any, at least in my view, at any SRT that we can get nitrification established. So we always try to optimize for SRT that favors nitrification, and the PAOs, because they're much faster growing organisms, will keep up. This is looking at, you saw this graph yesterday showing the nitrification temperature relationship, and here's phosphorus down in the bottom. So you see that, the SRT required for phosphorus removal is always underneath the curve of the nitrification curve. Be cautious, or certainly aware of recycled streams. They may be coming back from a variety of sources, but there's, phosphorus doesn't like to stay put. It likes to be on the move. You're going to get a lot of schooling on that from Leon later in the day and tomorrow. I want to just go through this quick exercise to have you think through now kind of a summary of stuff that we've talked about so far. And what we've got here is a fairly straightforward theoretical flow diagram that shows an anoxic compartment followed by an anaerobic compartment followed by an aerobic compartment. You've got that primary effluent now entering the reactor in this anaerobic zone. Secondary clarifiers over here, and RAS is coming back and entering this first anoxic reactor. So we're going anoxic, anaerobic, aerobic. And what we have here below it now is a graph. And it's compartmentalized to try to represent these different zones. And what I want you to consider is the fate of each of the compounds that are being transformed as we work our way through this flow scheme. So first we're going to take the carbonaceous BOD. Carbonaceous BOD. Why is the carbonaceous BOD low coming into in this part of the reactor, in that anoxic zone? Or another way I might ask that is, where does the carbonaceous BOD enter the treatment system? Your carbonaceous BOD is coming in right here, right? So if we look at the carbonaceous BOD, it's up, and under anaerobic conditions, what part of the BOD is actually being removed based on what you know so far? The readily biodegradable. Excellent. And who's doing that? Probably the PAOs, right? So this would be, we could call these maybe the VFAs, or you could call it the readily degradable fraction. But the BOD is being taken down largely then by the PAOs. What's happening to the BOD under in aerobic, the rest of the BOD? Who's doing that?
He's a heterotrophic one.
The other heterotrophic organisms, yeah. Any available food is fair game for all the other heterotrophs, right? So your BOD, I hope your BOD transformation or the carbon transformation is making sense. First kick at the can, the anaerobes, largely the PAOs, taking the easy stuff. The last kick at the can are the other heterotrophs finishing the job. Now, let's take a look at ammonia. why might there be a little uptick in ammonia? What is actually coming in to,
Nitrate.
but we're tracking ammonia at this point.
So you have maybe some type of denitrification and
Well, but does denitrification make ammonia? No, it doesn't. So there's no good explanation for a little uptick in ammonia, other than if we've got some cellular breakdown. When biology breaks down, it's like diapers in a diaper pail. You know, any TKN that might be released from cellular degradation can produce some ammonia. So I think if there is a plausible explanation for a little uptick in ammonia, it might be just the natural deamination of some of the TKN. Why is the ammonia higher?
we have the primary effluent load.
Because it's coming in the primary effluent, exactly. What's happening to why is the ammonia just pretty much a pass through?
Nothing happening in aerobic zones. So
Nothing happened in the anaerobic zone. Remember that the ammonia is in a reduced form. The transformation of it's got to be an oxidation. It's got to get oxidized. Is there oxygen in an anaerobic zone? No. So there's no real way to oxidize it. If there's any slight reduction, it might be associated with some uptake for some sort of cellular use by the metabolism that's going on there. But basically, ammonia is a pass-through. What's happening to the ammonia over here in the aerobic zone?
it changed, oxidized rather.
Yeah, it's being oxidized by who?
NOBs.
NOBs and ALBs, or ALBs and NOBs, or maybe a como B, a como box, right? But this is the nitrification reaction. All right, now let's take the nitrite numbers. Why is there nitrite coming into that basin? And why does it go to zero?
So that's where denitrifications happen to many of these people.
The denitrification that's happening. So apparently there had to be nitrate produced that's being carried back with the recycle sludge. You know, some of it left in the final effluent, and that was in the soluble in the part of that water column that becomes recycled is going back around, right? So does it make sense? Your nitrate is dropping to zero. There's no change from zero across the anaerobic zone. Nothing's going to happen there. And what's happening across the aerobic?
Well, now you're using ammonia to convert it into nitrite.
They're exactly right. Now they're using the ammonia. So this is nitrification. Let's look at the phosphorus. Okay. Very little change in phosphorus coming across the zone. Why does the phosphorus jump up?
Because you're releasing it down to first anaerobic, so the cells are consuming the BFAs or BOAs rather, and releasing that phosphorus.
Exactly. This is your phosphorus release, right? And what's happening here?
That's your left real.
Uptake. That's your uptake. Okay. They're making sense. So we've taken the carbon, we've taken the ammonia, we've taken the oxidized form, the NOx, and now we've taken the phosphorus. So when you go to take the certification test and they put that curve up there and they say, explain that to me, you can tell the story. Now, if we just get this and somebody says, that's BNR right there, that's all you need to know. It's just as simple as that. It's like, oh man, shoot me. You know, but the idea here is try to take these apart kind of one at a time, and with all the things that we talked about, I hope that that's making logical sense. Now, these plants always play out in real time. Just finish up with just a couple of real plants. This happens to be a plant that I've had the good fortune of being around for a number of years. In Montana, the Kalispell plant. Dr. James Bernard, who mentored Leon and who Leon has now stepped into the shoes of, certainly had a big hand in this particular plant is one of the early BNR plants that was designed and with a huge amount of flexibility. And I think part of that was, in the day, some uncertainty about how things were actually going to work. And so they really provided a lot of operational flexibility and compartmentalization and cross ties and valving that really allowed that plant to be a very good experimental, full-scale case study. And if you pick up books on BNR, you'll likely run into Kalispell as one of those that have been, I think a lot of things have been worked out in. If you happen to get up into Montana, the folks at the Kalispell plant love to have visitors. They're wonderful folks. If you're going to be in that area, take in Glacier Park. And if you can spend a few hours at drop down to the plant, I'm sure that you would enjoy that. But this is the aerial view of that. I took that and then put these graphics on top of it. So basically, this plant has a primary clarifier. It has flow equalization, and then the flow travels from 1 to 2 to 3 to 4 to 5, 6, 7, 8, 9, 10, 11. These are different compartments. The first two compartments, and this will look a little bit familiar to you folks from North Texas because it's a lot like Wilson Creek in that there's a pre-anoxic zone. Pre-anoxic is intended then to scrub out nitrate before that biomass that's coming back from the secondary clarifiers is coming in here before that biomass then gets into the anaerobic zone, so there's no nitrate, what they call nitrate poisoning. So it has a pre-anoxic zone, then some anaerobic cells, and then it has it goes into anoxic, a number of those, and then it goes into aerobic. You'll see that there's now a second stage down here. When this plant went through plant expansion, based on what they found, how this worked, they basically doubled the size of the plant with a much simpler flow scheme because now they had figured out routing and loadings and configurations that made the complexity of the original design unnecessary to completely replicate. But it's a very good case study. If you look at it from the side view, then this might make a little bit more sense then. They take primary effluent and it comes into a pre-anoxic zone. The RAS is coming back from the secondary clarifiers. And the RAS from the secondary clarifiers, which is carrying nitrate with it, and the carbon source from the primary and the VFAs that are being generated from the fermenter are the carbon sources that are driving off any nitrate. So that basically, you get nitrate to zero in this pre-anoxic. And then, of course, biomass is flowing into an anaerobic zone. This is where the poly P goes to phosphate. You get the phosphate release. The VFAs are forming the PHA or PHB, however you want to call that. And then once that occurs, it goes into an anoxic zone. That anoxic zone is created by an internal recycle where they pick up fully nitrified mixed liquor and pump it back around into this anoxic reactor. In that anoxic reactor, then, the nitrate is acting as the oxidizer of the carbon that's coming through that has not been taken up by the PAOs. And so you're scrubbing off a lot of nitrate then by denitrification. And then the flow goes on down into an aerobic zone where you're finishing off BOD removal, you're doing nitrification, and your phosphorus is being taken up. So that's Kalispell. This is this is Google gives me an aerial view of Wilson Creek. And I thank you folks for taking the time to come and join us. And I've had the privilege of getting to be at your plant for a short period of time. And I put this graphic together to try to make something that was useful for training purposes with your staff. So this is the part of the plant that was under modification. So I'm looking at now, looking down on parallel compartments here. And so what we have here at Wilson Creek then is pre-anoxic compartment. It's very similar to what you saw at Kalispell. Then you've got an anaerobic zone following that pre-anoxic. Then you've got an anoxic, just like Kalispell has, following that. And then you have aerobic following that. If we look at that at your plant, this was just one of your engineering drawings. And I just took it and tried to put them kind of in cross section so that we could see kind of flow pattern. Again, pre-anoxic goes to anaerobic, goes to anoxic, goes to oxic or aerobic. Okay, this is just a repeat of what we're looking at bird's eye now linearly. The RAS comes back into this pre-anoxic. The flow comes in and some of it's going into that pre-anoxic to feed. And if I get this wrong, I'm going to ask you to correct me when I'm done. I'll just pile through this. We're slipping some, at least my recollection at the time, we were slipping some BOD in here to drive denitrification to scrub the RAS. Ammonia is a pass-through and it's not converted in that pre-anoxic. In the anaerobic zone is where we're getting your phosphorus release, all in the same rules. Ammonia is a pass-through on the anoxic, on the anaerobic all the way through anoxic, and it's converted when we get to oxic. So this is consistent with the same thing that you just saw at Kalispell. Nitrate through internal recycle, through your internal mix like a recycle pumping, is coming back around into this anoxic zone and is being scrubbed off and goes off to atmosphere through denitrification. Phosphorus is being taken up in this oxic zone and is landing in the mixed liquor. So we've got the phosphorus now stuck into the mixed liquor. That goes to the secondary clarifier. Secondary clarifier is taking that right back then around the horn. The nitrate that's coming back with that is going to be scrubbed off again on the next pass through. And I hope I've got that right. The nitrate is leaving the system then in the second place, which is coming off of the nitrogen is coming off of that pre-anoxic. Now, straighten me out, Dan. Did we get that right? Nailed it?
Yeah.
Wow, I buy a lottery ticket today on my lucky day. So I will conclude. Number one, with thank you for being so gracious to sit through this. And if any of you are familiar with Richard Pressman, who wrote The Hot Zone, I think he summarized this nicely.
Yeah.
Kind of what I really made obvious during my work here with you in the last 2 days. And that, in biology, nothing is clear, everything is too complicated, everything's a mess. And just when you think you understand something, you peel off a layer and you find deeper complications beneath. Nature is anything but simple. Yeah, I think he nailed it. This, of course, was a book written about the Ebola virus and the problems that occurred from that particular microbiological event. But I think what's also apparent is there's pure magic and pure power and potential in the ability to transform carbon, nitrogen, and phosphorus in fairly remarkable ways with very natural forces that you put your hands on every day with your understanding of those 8 growth pressures and the way that you maintain and manipulate your plants really empowers Mother Nature to do what she can do best. None of this happens without getting our hands pretty darn dirty and doing some things that are not pleasant. Without y'all doing that, this would just be a theory that we keep in the book. The fact of the matter is, Trinity River is a remarkable body of water that shows the work that you do. Certainly the people at Texas may not give you all the credit that you do, but certainly have a right to be proud of protecting this natural resource. I hope what we've covered here on the basics give you a little bit more inclination to feel the importance. This is not a trick. This is from my heart. The importance that you have in making this happen. This does not happen without people showing up and doing their work over and over, rinse and repeat. And we're better off for it. Whatever you're making, I can tell you it's not enough. It never will be.
Can you call my boss?